This video will continue our discussion of polar integration by working another volume example. So we want the volume between, that first thing is a sphere, right, with radius 4. And then the second thing would be a cone, all right? So we're trying to figure out, we have a sphere intersected with a cone. We want the volume between them. You could plug these into a graph and you could see the volume. That wouldn't be a bad idea. But I kind of want to relate the two. I want to know the projection onto the xy axis so I can come up with potential polar coordinates. Okay, so I'm going to take the z of the second function and plug it into the first function. So I got x squared plus y squared plus the square root of x squared plus y squared. That whole thing is squared to equal 16. Right? If I work that out, okay, I got x squared plus y squared plus x squared plus y squared. The square and the square root are inverse operations, so they go away. I got 2x squared plus 2y squared equals 16. If I divide everything by 16, I got x squared plus y squared equals 8. So this is a circle, so let's draw this. Usually have this drawn beforehand. So we have our xy plane, and we're just going to draw a circle on it so we know what we're talking about. Doesn't really help a whole lot, but we have it there. This is y, this is x, and then I know it's a radius of square root of 8 or 2 rad 2, however you want to think about it. Okay, so we can convert that. I know that's going to help me with polar. I know I can do r now. R is between, we're talking about the region inside here, so where they intersect. R is between 0 and 2 root 2, and then theta is the whole circle. So 0 to 2 pi. Okay, cool. Our bounds are set. The problem is, remember, we have to do, in our integral, we're going to have, you don't need to write this down, top minus bottom, right? I need to have that, so I need to determine which one is top and which one is bottom. Well, first I need to get functions of z. The second one I'm good, but this one is going to be z, and they want volume between, so this is going to be above. It's going to be z equals 16 minus x squared minus y squared. We could even make that into polar. That's minus x squared plus y squared. So this is equal to the square root of 16 minus r squared. This other one is going to be z equals the square root of r squared, which is just r. Normally we would do an absolute value there. It would be important, but the way that r's are defined, typically we're going to define them as a positive r. Now, I know when you're taught this system, r can be negative. It just spits the other way. We're just going to go with the positive r here, though. I bet we could make a negative r and end up with something similar. I'm not going to mess with it, though. I'm just going to leave it the positive r and keep that straight up. All right, so I do top and bottom. Maybe it's a little difficult to see which one's on top and which one's on bottom. So we could plug a 0, 0 into both our functions. Well, if I plug a 0, 0 into this one, I get z equals 0, 0 is going to give me 4. If I plug 0, 0 into this one, I get z equals 0. So the top one, this is top, and this is bottom. All right, so we're going to do the square root of 16 minus r squared, and then it's going to be minus r times r dr d theta. R is running between 0 and 2 root 2. And then theta is running between 0 and 2 pi. All right, so we would have to work this out in a way with that. It really does work out when I multiply the r through. It's going to give me two integrals. One is just going to be negative r squared. Very easy to integrate. The other one's going to end up being, let's just multiply so you can see it. Theta equals 2 pi. And then I rewrite my bounds for this, 0 to 2 root 2. And then we're going to get r times the square root of 16 minus r squared. And then minus r squared. All that dr d theta. This is a u sub for that first one. I'm going to split my integrals to make it easier. Anytime I get a little insecure about it, I just do two integrals. So theta equals 0, theta equals 2 pi. And then I'm going to go ahead and split these. The reason I'm doing that is because when I do my u sub, I'd like to not have to go back. I'd like to change them to u's. So I'm going to do r square root of 16 minus r squared, dr d theta. All right, there's one of them. And then I'm going to go ahead and just minus this other, and we'll put them back together, but I like to do that for my u subs. I have a lot of students that will make mistakes and u sub the second one as well. Just be careful. If you can manage, kudos to you. Do it the way that you can do it, and hopefully I can follow your work. Okay, this is just a nice pretty u sub here. If I let u equal 16 minus r squared, then du is equal to negative 2r. I have an r to replace, so it's going to be a negative 1/2 du equals r dr. So it takes care of the r dr, and then we're going to put a half out front. So switch back. Okay, I got theta equals 0 to 2 pi. And then we can go ahead and do our u's here. If I plug in r, I get 16 here. If I plug in 2 root 2 to there, or I think square root of 8, I get 8, which is going to give me an 8 there. And then now I can change this to, this is just u to the 1/2. And then let's put our negative 1/2 out front that we have to add in. All right, du d theta. There we go. Now this one we can go ahead and start integrating. I got 0 to 2 pi. And then we get 1/3 r cubed. And then that's ran from 0 to 2 root 2. Or I actually like using root 8. I know everybody wants to switch it, but I like using it. It's easier. Okay, here, this is just a normal integral. I got negative 1/2. I got theta from 0 to 2 pi. And then we're going to go up by 1, that's 3/2, divide by the new one, so it's 2/3 u to the 3/2. And then we run this from u equals 16 to u equals 8 d theta minus, and then I'm just going to put these back together after I plug in everything. So theta equals 0 to 2 pi. If I plug in the cube root of 8, I get 8 out. I get 8/3 cube root of 8 d theta. Actually, I'm not going to put these back together. That's a nice pretty constant. There's no reason for me to do that. So here we have our, we're close to our last integral. We got negative 1/2. 0 from 0, theta from 0 to 2 pi. And then I plug 8 in. Okay, I get 2/3. 8's not going to work out nicely at all. The 16 does. I get 2/3, and we get 64 is the 3/2 power for that. The square root of 16 is 4. 4 to the third is 64. But I still got a d theta here. I'm going to go ahead and this one is going to be very easy. Right, the 0 will just go away, so I have that. We have our last integral here. I got negative 1/2, and then it's going to be 2/3, 8 3/2 minus, okay, 64, that's not clean at all, so it's in 128 over 3. And then we run it from 0 to 2 pi. You can see how that's going to work out. And then we got minus, I'm just going to leave this, we can actually make it 16 pi over 3 root 8. Okay, the last thing we can do is multiply that negative 1/2 through and times it by 2 pi because I'm going to get a theta out of that constant. So I got negative 1/3, 8 3/2 times 2 pi. All right. And then minus, or plus, because we're going to have times it by a negative. And I got 128. I don't care about reducing this. It's going to be over 6. I think it does by 2 for sure, times 2 pi. And then minus 16 pi over 3 root 8. Sorry for getting the edge there. I ran out of room. But that's just plugging it in. It's no big deal. You could also, at some point, once you get down to just one variable, where does that end up? Well, it's kind of a mess all over the place. But that's our exact answer. You could type that in your calculator and get an approximation, a number that maybe makes a little more sense to you. Again, these integrals I'm throwing at you in my lectures are a little bit are tough. I wanted to model these, that way when you go off to your homework, maybe the integrals that were within homework may not feel so bad.